Greetings everyone. I'm Prathami and I welcome you all to another new episode of the 24th Universe channel. In this video, we will see all about Karnaugh Map. What is Karnaugh Map? Knowing the useful terms. What are the rules? Understanding Karnaugh Map with an example. What are don't care conditions in Karnaugh Map? What are race hazards? Pros and cons of Karnaugh Map. And last assignment for you. Let us first see what is a Karnaugh Map. Karnaugh map or K-map or KM is a graphical representation of a truth table that can be used to simplify Boolean algebra expressions. It results in less number of logic gates and inputs to be used during the fabrication. Here are the examples of 3 variable and 4 variable Karnaugh maps. Fabrication means manufacturing something but with a slight difference. That is, fabrication involves combining different standardized parts available to form a finished product, whereas manufacturing is taking raw materials and putting them through a process to create a finished product. In a simple language, for a beginner to understand, fabrication is a cooking process. Say, in order to make bread, we choose from the kitchen the available resources which are already in processed form like all purpose flour, salt, sugar, oil, yeast, and water, and then processes such as kneading, rising, and baking is done to finally get the finished product, bread. Similarly, for making semiconductor devices, we choose the available resources such as silicon wafers, germanium wafers, gallium arsenide, indium phosphide, and doping impurities like boron and phosphorus, and then various organized processes such as thermal oxidation, photolithography, etching is carried out to get the finished product, that is semiconductor device. Logic gates are formed by connecting transistors together on a semiconductor material to make an integrated circuit. The wafers or chips of semiconductor contain a lots of logic gates that make up different types of devices which work together to read, store, calculate, and transmit digital information. Now let us get back to our topic. In Boolean algebra, any Boolean function can be expressed in the standard or canonical disjunctive normal form, that is CDNF, mean term canonical form, or sum of products, that is SOP, as a disjunction of mean terms. Also, it can be expressed as the De Morgan dual, that is the canonical conjunctive normal form, that is CCNF, maxterm canonical form, or product of sums, that is POS, which is a conjunction of maxterms. Other forms are Blake canonical form and its dual, algebraic normal form, also known as Reed-Muller. Mean term is the product of n distinct variables. It is also known as the product term. Each uncomplemented variable is indicated by 1 and each complemented variable is indicated by 0. The mean term is represented by m. To represent a function, we perform a sum of mean terms, also called the sum of products, that is SOP, and this function is represented by a small letter f. Example, consider 3 variables a, b, c. In this function f, a, b bar, c, a, b, c bar, and a, b, c are the 3 mean terms. How to map the mean term in Karnaugh map? Step 1. Identify the mean term or the product term to be mapped. Write the corresponding binary numeric value, that is a step 2. Step 3. Use binary value as an address to place a 1 in the K-map, and then repeat steps for other mean terms. Consider an example. The product term to be mapped is f is equal to a bar bc bar plus abc. The two mean terms are a bar bc bar and abc. So the corresponding binary value is 0, 1, 0 and 1, 1, 1. And so We put a 1 in the cell 010 and 111 in K-map like this. Maxterm. Maxterm is a sum of n distinct variables. It is also known as a sum term. Here, each uncomplemented variable is indicated by 0 and each complemented variable is indicated by 1. The maxterm is represented by capital M. To represent a function, we perform a product of maxterms, also called as the product of sum, that is POS. Let us indicate that maxterm function with capital F. Consider an example: a plus b bar plus c, a plus b plus c bar, and a plus b plus c are the maxterms. How to map the maxterm in Karnaugh map? Here also the 4 steps are: identify the sum term to be mapped, write corresponding binary numeric value, use the binary value as an address to place a 0 in the K-map, repeat for other maxterms. Consider an example. The sum term to be mapped is f is equal to a plus b plus c bar ended with a plus b plus c. The two maxterms are a plus b plus c bar and a plus b plus c. So the corresponding binary value is 001 and 000. And so we put a 0 in the cell 001 and 000 in the Karnaugh map like this. Sum of product SOP. In sum of products, various product terms, also called as the mean terms, are combined together with an OR operator and are used to interpret outputs with logic 1 combination. Example: consider the sum of products expression. In this, A B bar C is 101, A B C bar is 110, and ABC is 111. That is marked in respective cells in K-map. Product of sum, that is POS. In product of sums, various sum terms, also called as the max terms, are combined together with an AND operation and are used to interpret outputs with logic 0 combination. Example: let us represent the POS function with capital F. In this, A plus B bar plus C is 010, A plus B plus C bar is 001, and A plus B plus C is 000. The next is types of Karnaugh maps. A Karnaugh map will have 2 raised to n cells or squares, where n is the number of variables in the Boolean expression. So, based on the number of variables, Karnaugh map can be classified as 2 variables, 3 variables, 4 variables, 5 variables, 6 variables Karnaugh map, and so on. But out of this, widely used are 2, 3, 4 variable Karnaugh map. 5 and 6 variable Karnaugh map is a little bit difficult to process but is manageable. But beyond 6 variable Karnaugh map, processing Karnaugh map becomes extremely difficult. The main reason Karnaugh maps are not commonly used for more than 6 variables is the exponential increase in the size and complexity of the map as the number of variables grow. For 6 variables, the Karnaugh map has 2 raised to 6, that is 64 cells, which is still manageable. However, for 7 variables, the K map would have 2 raised to 7, that is 128 cells, and for 8 variables, it would have 2 raised to 8, that is 256 cells. The larger the K map, the more difficult it becomes to visually identify and group the essential prime implicants, which is a key benefit of using K maps for simplification. As the number of variables increase, other techniques such as the Quine-McCluskey algorithm or Patrick's method become more practical and efficient for simplifying Boolean expressions. One variable Karnaugh map will have 2 raised to 1 cells, which is equal to 2 cells. Therefore, it may be thought of as like this. In case of one variable Karnaugh map, simplification is not applicable. Say for instance, you have an expression f is equal to a, or say f is equal to a bar, and I ask you to simplify this expression. Make no sense, right? Consider another instance. Do you think we can further simplify the circuit? No. So we directly start with 2 variable Karnaugh map. Two-variable Karnaugh map. A two-variable Karnaugh map has 2 raised to n, that is 2 raised to 2, that is 4 cells. So, two-variable Karnaugh map represents 4 minterms or 4 maxterms. These are the examples. Three-variable Karnaugh map. A three-variable Karnaugh map has 2 raised to n, that is equal to 2 raised to 3, that is 8 cells. So, three-variable Karnaugh map represents 8 minterms or 8 maxterms. These are the examples. Both these forms are correct and you can use any which way you are comfortable with, and it will result to same simplified answer. Four variable Karnaugh map. A four variable Karnaugh map has 2 raised to n, that is 2 raised to 4, that is 16 cells. So, four variable Karnaugh map represents 16 minterms or 16 maxterms. These are the examples. Sometimes you might see the index representation like this. It doesn't make any difference. Both ways are correct. 5 variable Karnaugh map. A 5 variable Karnaugh map has 2 raised to n, that is 2 raised to 5, which is equal to 32 cells. So, a 5 variable Karnaugh map represents 32 minterms of 32 maxterms. The 5 variable Karnaugh map is made using two 4 variable Karnaugh maps. When a is equal to 0, the left Karnaugh map is selected, and when a is equal to 1, the right Karnaugh map is selected. 6 variable Karnaugh map. A 6 variable Karnaugh map has 2 raised to n, that is equal to 2 raised to 6, which is 64 cells. So a 6 variable Karnaugh map represents 64 minterms or 64 maxterms. It can be represented like this. Now let us see rules for Karnaugh map. Now by looking at the Karnaugh map, we should be able to write the simplified Boolean expression. So for that we should be able to group the ones or zeros if it is a product of sums. Now how to group ones? Just remember 8 rules. Rule number 1. All the ones in Karnaugh map must be covered and made into group. Rule number 2. Number of cells in each group should be a power of 2, that is, group can be made of 1 cell, 2 cells, 4 cells, 8 cells, 16, 32 and so on. Rule number 3. Grouping may overlap. Rule number 4. Grouping of ones with zeros is not allowed. Rule number 5. Groups may wrap around. That is, uppermost and lowermost cells can be made into group, and also rightmost and leftmost cells can be made into groups as they are adjacent, that is, 1 bit difference. Same goes for the corner cells. Rule number 6. Group should be as large as possible. No Boolean laws are broken, but it would not be sufficiently minimal. Rule number 7. Groups can be made vertically or horizontally, but not diagonally. Rule number 8. Don't care should be included while grouping to make a larger possible group. It is represented by letter X. We will look at the don't care condition in some time, but for now just remember this rule. Now let us understand the Karnaugh map with an example. The best way to understand how a Karnaugh map works is to see it in action, and it all begins with a Boolean function. Consider an example, a Boolean function with 4 input variables a, b, c and d. F of a, b, c, d is equal to a bar b c bar d plus a b c bar d bar plus a b c bar d plus a b c d plus a b c d bar plus a b bar c d plus a b bar c d bar. So, in order to understand this Boolean expression, we should construct a truth table with 4 variables a, b, c and d. Each variable will have separate column. The last column will list the function's returned value for each combination of ABCD inputs. Fill out the values 0 to 15 in binary like this. To make it easy for a beginner, the table also includes a column that contains a decimal equivalent number for each row. This will make it easy to track and reference various combinations. Once you have mastered the K-map, no need of this decimal column. Since we are familiar with the terms like minterms and sum of products, I will use it here. The given Boolean function is in sum of products form. So, in the minterms, each uncomplemented variable is indicated by 1 and each complemented variable is indicated by 0. that is in A bar B C bar D. A bar is equal to 0, B is equal to 1, C bar is equal to 0, D is equal to 1. So put 1 in F column for these combination of inputs, that is 0 1 0 1 is equal to 1. Next is A B C bar D bar means 1 1 0 0. So put in truth table 1 for 1 1 0 0 combination. Similarly, fill the F column and all the unfilled rows are marked with zeros like this. With this truth table, we cannot simplify the original expression. So now we need the Karnaugh map and can be easily built from the truth table. Remember, once you have perfected, you can build the Karnaugh map from the Boolean expression directly. And this is how we build the Karnaugh map for 4 variables. In order to populate the Karnaugh map with the ones and zeros, we should look at the truth table. For easy reference, the cells are also numbered, so write 1 accordingly. After some practice, you can do it by just checking the input combinations of ones and zeros. 0 0 combinations in truth table have a 0. So in K-map, for 0 0 0 0 combination, we mark the cell with a 0. Here in truth table, row 5, 10, 11, 12, 13, 14 and 15 has the output value 1. So fill in Karnaugh map cell numbered 5, 10, 11, 12, 13, 14, 15 with a 1 and mark 0 in the remaining cells. If you do not wish to use the truth table, then use this method to fill K-map cells. That is A bar B C bar D is 0 1 0 1, A B C bar D bar is 1 1 0 0, A B C bar D is 1 1 0 1, A B C D is 1 1 1 1, A B C D bar is 1 1 1 0, A B bar C D is 1 0 1 1, A B bar C D bar is 1 0 1 0. Now we have to group all the ones according to the rules that we have already discussed earlier. So according to the rules that we have already discussed, we can make 3 groups in Karnaugh map like this. Once the groups are identified, the final expression can be calculated as follows. For each group, in which variable do not change using the row and column binary labels or indexes. For group 1, AB index value remains the same, but C and D index values change. So omit C and D values in the expression. So group 1 results to expression AB. For beginners, you can use this method. Just write ABCD and below write the combinations for 1, that is 1100 from K-map. Next is 1101, next is 1111 and last is 1110. Now cancel the variables that are changing in binary values like this. Hence, the final expression in group 1 is AB. Similarly for group 2, this is it. The expression is AC. And for group 3, the expression is BC bar D. So, the simplified expression of the given Boolean function f is equal to AB plus AC plus BC bar D. Isn't it great? We didn't have to go through all the laws and simplifying overhead. Now let us see what are implicants, prime implicants and essential prime implicants. Implicants can be understood as all the individual elements of each cell in the Karnaugh map. Implicant refers to any product term or mean term in the SOP, that is sum of products form, or sum term or max term in the POS, that is product of sums form of a Boolean function. Prime implicants is the smallest possible product term in SOP form or sum term in POS form of the given Boolean function, where eliminating any one element is not possible. Essential prime implicants is a prime implicant that should hold at least one mean term that is not included by any other prime implicant. This can be better understood with an example. Consider a 4-variable Karnaugh map ABCD as follows, and that is already mapped in sum of products form. Here, the implicants are A bar B C bar D bar, A bar B C bar D, A bar B C bar D, A bar B bar C D, A bar B C D, ABC bar D, ABCD, ABCD bar, and AB bar C bar D. There are total number of 8 implicants. Prime implicants are A bar B C bar, A bar C D, ABC, AC bar D, and BD. Total number of prime implicants are 5. The essential prime implicants are A bar B C bar, A bar C D, ABC, and A C bar D. Total number of essential prime implicants are 4. What are don't care conditions in Karnaugh map? In digital logic, a don't care term abbreviated as DC for a function is an input sequence, that is a series of bits for which the function output does not matter. Here in Karnaugh maps, don't cares act as wildcards. It is similar to a joker card used in rummy game. How a joker card can be used to complete sets if a player is missing a card. In the same manner, the don't care conditions allow us to replace the empty cells of a Karnaugh map to form a large group of the variables. Don't care conditions are typically represented by an X or a cross mark symbol in a Karnaugh map cell. These cells are treated differently during the minimization process. That is, while forming group of cells, we can consider don't care cells as 1 or 0, or we can totally ignore that cell. The difference between don't care in Karnaugh map and don't care in BCD. They are same. For a beginner to understand, in BCD, we just name it, but in Karnaugh map, we process it. That is, in BCD, the invalid combinations are represented with don't care X in Karnaugh map. In Karnaugh map, these don't cares are used to make larger groups and hence to simplify the Boolean expression. The don't care conditions may arise in various scenarios. Invalid input combinations. When certain input combinations are not valid or cannot occur in the specific circuit application. For example, in a 4-bit binary coded decimal, that is BCD system, the values 1010, 1011, 1100, 1101, 1110, and 1111 are not valid BCD codes. These invalid combinations are don't care in the Karnaugh map. Design flexibility. The designer might not care about the output for certain input combinations, allowing for more flexibility in circuit design. Now let us see an example of Karnaugh map with don't care condition. Consider an example, the following Boolean expression, where small m represent the mean terms and small d represent the don't cares. Here is the Karnaugh map representing the mean terms and the don't cares, and the rest of the cells will be occupied by 0. This is how the grouping is done. We consider the X in 1110 cell, that is 14th cell, as 1 and make a group of 4 cells, that is indicated here by red color. And also the X in the 1010 cell, that is 10th cell, is treated as 1 to make a group of 4 cells, which is indicated by blue color. And the reduction will result to the simplified expression F is equal to B D bar plus B bar C. It is not necessary that we have to cover all the don't cares to make groups. We can leave the don't cares as it is in the Karnaugh map if not required. What are race hazards in Karnaugh map? In general, a race condition or race hazard is the condition of electronics, software, or other systems where the system's substantive behavior is dependent on the sequence or timing of other uncontrollable events, leading to unexpected or inconsistent results. It becomes a bug when one or more of the possible behavior is undesirable. By making use of the Karnaugh map, we can clearly look out for such race hazards and eliminate it well in time, in turn eliminating the race hazards or glitches in digital electronics. Let us understand this with an example. Consider a sum of products expression y is equal to summation of m of 0, 2, 3, 5, 6, 7, 8, 9. Here is the Karnaugh map for it with mean terms, and this is how we can group according to the rules. Now we can clearly see that the cells 0, 0, 0, 0 and 0, 0, 1, 0 are adjacent cells and are not grouped. So they might cause race conditions. So in order to overcome this condition, just make them into group and include another product term into the Boolean expression. So the simplified Boolean expression with race conditions is resolved. And the expression is f is equal to a bar c plus a bar bd plus a b bar c bar plus b bar c bar d bar plus a bar b bar d bar, and this is the respective logic circuit design. This additional term would not do anything but just be there to save us from the glitches that might arise in later. This additional term is similar to an earthing system that prevents us from getting an electric shock in an electric circuit. Now let us see the pros and cons of Karnaugh Map. That is the good things and the bad things about the Karnaugh Map. The good things are it simplifies the Boolean expression without having to use the Boolean laws or algebraic computation, and hence minimizes the number of logic gates used. And we just now saw that it is very easy to identify the race hazards on Karnaugh Map. And the bad things are it is not suitable for computer reduction, and also it is not suitable when the number of variables exceeds 4. That becomes extremely difficult. Now I have an assignment for you. Here is the 7-segment display and the respective truth table. Now you have the idea of the Karnaugh map and the truth table, so you can solve the problem on your own. I would like to give you a hint. You're going to need 7 different Karnaugh maps, one for every segment, that is A, B, C, D, E, F, and G. And that's a wrap on this. I hope you have understood something over here. If you have any queries, you can drop it in the comment section below. I will surely respond. Also, don't forget to share this video with your friends and family who might need this. And if you have not subscribed, then please do it because more such contents will be uploaded soon. Thanks for watching and see you soon in my next video.